Hello everyone, this is going to be another fluids/thermo video, and in this video I'm going to be going over a manometer problem. So as you can see, I've drawn this manometer above. So what's going on is we have point 1, which is enclosed with natural air all over to the left here, and then to the right we have point 2, which is exposed to the ambient air as well. So from point 1 to point 2, we have a total of 3 fluids in this manometer. So our goal is to find the pressure at the opening, which is the pressure at point 2 over to the right here. Okay, so kind of to start off this problem, I like to write down the properties that we have. So let us begin. Okay, so some properties, or another word for it is givens. So what we're given in the problem. So let's say we were given the density of water. I didn't write that, but let's say we were given this. Okay. We also know the specific gravities. So we know the specific gravity of A is 12.4. And we know the specific gravity of B is 0.8. Specific gravity of C is 1. And we actually have an equation as well. So let us recall specific gravity equation, which is equal to simply the density of whatever object you're interested in divided by the density of water. Okay, so if we did want to find densities, so for instance, density of A would just be the specific gravity of A multiplied with the density of water. So then we get the specific gravity, the density of A as 12,400. This is kilograms per meter cubed. Okay, and similarly, density for B, 0.8 times 1,000, which is the density of water. We get that the density of B, the fluid B, is 800 kilograms per meter cubed. And then finally, density of C is just going to be the specific gravity, which is 1 times 1,000. So we know that the density of C is actually just water. Or in other words, fluid C is water. Okay? So from here, I also like to write down my assumptions. So let's write that down as well. So some assumptions for this problem. So we're going to go ahead and say that these fluids are incompressible. Okay, and then we're also going to say that the pressure in the natural air is uniform. So what I mean by that is, so if we have a glass here of some fluid, what I'm trying to say is at any location, even at any height along this fluid, the pressure is going to be the same. So if this was air, we know that the pressure is just going to be ATM, atmospheric pressure. So what I'm trying to say is, even if this location is higher than this location, the pressures will be the same because we're assuming that the pressure is uniform. Okay, and that's a good assumption to make, so long that the density is really, really small. So that's why we can do that with air. All right, so from here we can actually now try to solve this problem. So I'm going to do that off to the right here. This is going to be our analysis. Okay, so we can set this problem up by choosing a beginning and ending point. So for instance, we'll just say we're going to start here at 1 all the way at the left. So that's our beginning point, and our ending point is going to be 2 off to the right here. So we then say that P final, so when we do these kinds of problems, we put the final point, which we know is just P2. pressure at 2. And we set that equal to the unknown, which the unknown would be substituted from starting off on point 1, climbing over to point 2. So for instance, we say that the pressure final, which is P2, is going to equal, and then we would travel from point 1 and travel along your manometer, either adding or subtracting pressures from each fluid until you get to the final location, which is right there. Okay, so let's just walk through that. So P2 is equal to, so I'm going to use yellow. So as of right now, we're right here. Okay, so the pressure at that location is PATM. So I put PATM in there. And then, so natural air, it's uniform until we get to the fluid A here. So from here, since we're going, since we have to go up in height, we know that the pressure is going to drop as you go up. So now we have to subtract the pressure drop from fluid A. Okay, and then so now after that, we're up here, or better yet, right here. So now we've encountered fluid B. So with fluid B, our height is going to be going down. So we're going to start here and we're going to end up down here. So it's a net decrease in height, which means the pressure would increase. So then we'd add the pressure from fluid B. So now we're at this location. And then from here, we're at fluid C. We've encountered fluid C. And fluid C goes from this location all the way up to point 2 here. So that's a positive height change, which means the pressure is going to be negative, so minus PC. All right, and then, so now technically we're up here where fluid C ends and the atmospheric is in contact with fluid C. So technically at that point, we don't need to do anything else because that's our final location. Even though this says 4 centimeters, it doesn't matter because the pressure is uniform since this is just air, meaning that the pressure here and the pressure up here are the same. So we are done with this problem here. So from here now we need to figure out what those pressure terms are. So recall from fluids that the pressure of any fluid is just rho times G times H. So now we can actually substitute those terms in. So let's do that here. Okay, so P2 is still unknown. PATM is actually 101,325 pascals. PA is rho A times G times the height of A, which is 8 centimeters. So 8 times 10 to the minus 2. And then PB, pressure at B, is density of B times G. And then the height is going to be, or for B, I should say, is going to be 29. So this is actually, sorry, it's actually supposed to meet up here. So that's at the same location there. Okay, so the height is, for the red fluid, fluid B, the height change would be 29 centimeters, which is this height, subtracted from the 12 centimeters here. So that's going to give you the difference here. So 29 minus 12 times 10 to the minus 2 to get that in meters. And finally, pressure at C, which is going to be the rho at C, which is, we know it's just water, times G times 29. So the height change is just 29. That's just given here. Okay, so with that, we have all our values. We have all these rho values. We've calculated them already. And we know G is just 9.81. So if we go ahead and solve for pressure, we get that pressure 2 is actually equal to 90.08 274, and that's going to be in kilopascals. So this right here is going to be the pressure at the opening, which is also the pressure at point 2 off to the right here. Okay, so yeah, this is just pretty straightforward with manometers. Like I said, you would start off the problem with writing your final location first and setting that equal to starting at the beginning and marching along through the manometer up until you get to that point, which is what we did right here. And then from there, you just substitute the pressure values for each fluid. All right, I hope you guys enjoyed this video. See you in the next one.